Okay, welcome all. Today we are going to discuss the topic that is the various addressing modes of 8051 and explanation of each addressing mode with a example. Each instruction requires certain data on which it has to operate. Right? If you can remember, that is the instruction format we have discussed in the last video lesson is opcode followed by operand. So every instruction generally has this format, that is an opcode followed by an operand. Second point, the data could be in register or registers, in memory, or an immediate value. The data can be any of this. It can be stored in the registers. We have general purpose registers A, B, and R0 to R7 of each bank, and other important SFR registers also there. And in the memory, directly we can point out to the memory address where the data is stored, and it can be an immediate value, that is directly supplying the data value, that is directly writing the data in the instruction itself by differentiating the address and data value by using the hash symbol. The third point is the various ways of accessing data are called the addressing modes. So why we need these many number of addressing modes? Because we can store the data in the memory, or it can be in the registers, or it can be directly supplied in the instruction. So various ways of representing the data, different modes are available. So depending on those modes, we have different addressing modes available. The fourth point is the 8051 microcontroller has the following addressing modes. Names. First one is the immediate addressing mode. Second one is direct addressing mode. Third one is register addressing mode. And fourth one is register indirect addressing mode. Fifth one is index addressing mode. And sixth one is register specific addressing mode. Now let us start with the first addressing mode, first type of addressing mode, that is immediate addressing mode. In this addressing mode, the source operand is a constant, that is immediate data, whether it can be 8-bit or 16-bit. In this addressing mode, the source operand is a constant. Examples: move a comma hash 47h. This is an instruction in which the data 47 hexadecimal number will be moved onto the register A, that is accumulator register. So that is what specifying the load 47h into A. Next one is move R4 comma hash 67h. Move R4 comma hash 67h. In this, the data 67 is loaded into the register R4. So load 67h into R4. Next, move dptr comma hash 8500h. 8500 is a 16-bit data, and dptr is also a 16-bit register, so they are matched. So the 16-bit data will be moved on to DPTR. So by observing this, we can represent the immediate data either 8-bit or 16-bit also. Note, the immediate data must be preceded by the pound sign. It's not pound, it is pound, POUND hash. Using this addressing mode, we can load data into the any of the registers, including the DPTR. Including DPTR, why we call? Because DPTR is a 16-bit register. It is external register. Sorry, to access the external data. This is the easiest addressing mode to transfer the data to destination. That is, move a comma hash 47h. In that, a is the destination and hash 47 is the source. The source operand is, see the first point in this addressing mode, the source operand is constant. So in the examples also, if you see, move destination comma source, that is the format of move instruction, and that we have the source operand is hash 47, hash 67 and hash 8500h. So these are all the constants. That is, the user is supplying the data in the instruction itself, whether the destination in these instructions, that is a comma r4 comma DPTR. Those are the registers, general purpose registers and some special purpose registers. So the hash symbol should be there. And the fourth point is, the general format of immediate addressing mode is move a comma hash nh. So this is the format: move a or any register, move register comma hash nh, where n is the 8-bit data, and the same can be represented in the next instruction: move dptr comma hash double nh, where double n is the 16-bit data. Why? Because we have used dptr register. In the third instruction below the dptr instruction, we have move r3 comma hash 125h. That is 12-bit number, right? Hexadecimal, each digit is equal to 4-bit number. If we represent it in a binary, then 3 hexadecimal numbers will be equal to the 12-bit. So it is illegal instruction because source and destination sizes are mismatched, right? Because R3 is a general purpose register and it is a 8-bit register. Whether in the source we have 125 hexadecimal number, that is a 12-bit binary number. So 8-bit is the destination, 12-bit is the source. So it is match, right? So that is a illegal instruction. And next instruction, move 35h comma hash r2. Move 35h comma hash r2. See whether is it correct or not. These are all the illustrative examples. We can write many of these instructions, but whether we have to see they are following the syntax and the move instruction format, and whether it is immediate. To represent the immediate addressing mode, you have to follow certain rules, right? Hash should be followed by a constant only, where r2 is not a constant, it is a register. And the source and destination registers size should match. So below the move 35h comma hash r2 instruction, we have it is illegal instruction because source should not be register, it should be data. And next move r0 comma 33h, but that means we are missing the hash sign. What happens if we miss the hash sign? It is not the example of immediate addressing mode instruction because there is missing of symbol hash, but the instruction is correct. Move r0 comma 33h is a valid instruction, it is not illegal, which I didn't say it is a illegal. It is a legal instruction, but it does not do what we intended it to do. That means if we want to represent an immediate addressing mode type of instruction, then we should use hash compulsorily. If we don't use it, it may be another addressing mode. Okay, so in a summary point, if the immediate addressing mode has to be used, then there should be a hash sign followed by a constant and the sizes should be matched. The second type of addressing mode, that is direct addressing mode. In direct addressing, the operand is specified by an 8-bit address field in the instruction. This mode is used to access data either in the internal RAM or SFRs. SFRs means special function registers. Okay, so the second point, this mode is used to access data either in the internal RAM, that is 128 bytes, or SFRs. Examples: move r0 comma 40h, save content of RAM location 40h in r0, save the content of RAM location 40h. 40h is the address, in that we have the data. That data will be moved into the register r0. So in the instruction we are mentioning only the address, not the data, but we are mentioning the data in which, we are mentioning the address in which we have the data, we have the required data. Okay, that is direct addressing mode. Second example, we have move 56h comma a, that is save content of a in RAM location 56h. Move r4 comma 7fh, move contents of RAM location 7fh to r4. 7f is the last RAM location in the on chip, because we have in the on chip only the 128 bytes. 7f is the last thing, 0 to 7f. Note, only internal data RAM and SFRs can be directly addressed. Although the entire 128 bytes of RAM can be accessed using direct addressing mode, it is most often used to access RAM locations 30h to 7fh. So in the notepad we have seen that is only internal data RAM and SFRs can be directly addressed. Although the entire 128 bytes of RAM can be accessed using direct addressing mode, most often we use 30h to 7fh. If you remember the internal memory organization of 8051, in that the 128 bytes RAM is divided into 3 segments. In that, the below segment up to 32 bytes are occupied by the banks, register banks, R0 to R7 of bank 0, bank 1, bank 2 and bank 3. After that we have bit addressable area. Then after that we have scratchpad memory, that is from 30 to 7fh. This is due to the fact same whatever I have explained now is represented in this point. This is due to the fact that register bank locations are accessed by register names of R0 to R7, but there is no such name observed for the RAM locations 30 to 7fh. Right? The lower 32 bytes are occupied by this register bank, so we can directly call them as R0, R1, R2 up to R7 instead of their memory location. Third point is stack in 8051 uses only direct addressing modes, that is only direct addressing mode is allowed for pushing or popping the stack. So in the stack we will have two operations, right? Pushing the data onto the stack and popping the data from the stack. So for both operations we use only direct addressing modes. The general format of the direct addressing mode is opcode followed by direct address. Push A. This is the example for the pushing of data onto the stack pointer. It is we are copying the data presented in accumulator register onto the stack. It is an invalid instruction because push and pop instructions must be used direct addressing mode. Push 05EH is the valid instruction, that is we have to mention the direct address in the push and pop instruction, not the registers. So that is the direct addressing mode. Just a quick recap. In a direct addressing mode, the operand is specified by an 8-bit address filed in the instruction. The mode is used to access data either in internal RAM or SFRs. Examples: move R0, 40H, save the contents of 40H in R0, and move 50H, A, save the content of A in RAM location 50H, 6H, and move R4, 7H, move the contents of RAM location 7H into R4. So only internal data RAM and SFRs can be directly accessed, although the entire 128 bits of RAM can be accessed, but most often we use RAM locations 30 to 7fh because below 30 we have the register banks lower 32 bytes, and after that bit addressable area is there. So the stack will be used only the direct addressing modes for pushing or popping operations. And the syntax, the general format of the direct addressing mode is opcode followed by direct address. Push A, it is a invalid instruction because push and pop instruction must be used direct addressing mode. Push some address, 8-bit address in case is the valid instruction. Now moving on to the register addressing mode. Register addressing mode involves the use of registers to hold the data to be manipulated. So the instruction will mention the registers in which the data is present. In this mode of data, in this mode, the data which the instruction operates on A, B, dptr or is one of the 8 registers labeled as R0 to R7, and Rn is in general. If you want to represent the R registers, that is R0 to R7, if you want to write general term for these registers, you can write with R with subscript n. So that will represent the registers. Examples are move A comma R0. Copy the contents of R0 into A register. Move R2 comma A. Copy the contents of A into R2. So both the source and destination are registers only, and the register size must be matched. And add A comma R7. Add the contents of R7 to the contents of A. And the next point is the source and destination registers must match in size. Yes, that has to be done, otherwise it will show an error. Then second point, the movement of data between R and registers is not allowed. See, this is important, because you may think that registers R0 to R7, we have multiple registers. You may think that we can directly copy the data from register R0 to R7 or R0 to R7 or R1 to R7 or R2 R3 like that, but that is not allowed. So we should use only A comma B and dptr and R0 to R7 one side. That is, in the source if you use R register, in the destination we cannot use this R register. The general format, that is the third point in the slide, I am reading. The general format of register addressing mode is to represent the instruction, that is syntax. How to write the syntax? Move RD comma or S. Where RD is destination register and RS is source register. And the fifth point is move dptr comma A. That is an illegal instruction, because the source and destination registers are mismatched in size. Why? Because dptr is a data pointer register which is 16-bit length, and A is a accumulator register, that is a general purpose register. It will have only 8-bit size. So this is a illegal instruction. You may think that both are registers, so why can't we use this two registers in the destination register and source register place of this register addressing mode? But it is mismatched and it is illegal. Move R1 comma R2, right? This can also be possible, but it is a illegal instruction, because the movement of data between the registers of register bank is not allowed. Because in the register bank we have R0 to R7, 8 registers will be there. We may think that copying of this R0 to another register is possible, but it is not allowed in this addressing mode. Move R1 comma R2, R2 comma R1, R3 comma R4. So those are all illegal instruction because it is does not allow like that. So this is the register addressing mode. And the register addressing mode involves the use of registers to hold the data to be manipulated. The registers will hold the data. In this mode, the data which the instruction operates on A, B, DPTR is in one of 8 registers labeled as R0 to R7. That is, we can simply write Rn. So move A, R0. Copy the contents of R0 into A. Move R2, A. Copy the contents of A into R2. Add A, R7. Add the contents of R7 to contents of A. And what will happen to the final result? Where it is stored? Guess, I have already taught you about this instruction. That is, every arithmetic instruction, the final result will be stored in accumulator register. And these are the additional points regarding this addressing mode. Source and destination register must match in size. Movement of data between R and registers is not allowed. General format of register addressing mode is move RD, RS, where RD is the destination registers and RS is the source register. Move DPTR, it is an illegal instruction because of size mismatch. Move R1, R2 is an illegal instruction because it does not allow such type of movement. Next addressing mode is register indirect addressing mode. Register indirect addressing mode. In indirect addressing, the instruction specifies a register which contains the address of the operand. Both internal and external RAM can be directly addressed. Can be indirectly addressed. Both internal and external RAM can be indirectly addressed. Examples: move A, at the rate or not. Move A, at the rate or not. That is, move contents of RAM location whose address is held by R0 into A. Read it again. Move A, at the rate or not. Move the contents of RAM location. Move the contents of RAM location whose address is held by R0 into A. That is, R0 is a register. In that register, we have some data. We have some information, that is bits. That bits will represent some address. That bits also represent some address in the internal memory, and in that address we will have the required data. It is indirectly mentioning the address of the data. So the data is indirectly mentioned in the instruction, and that has to be moved into the accumulator register. Second example is move at the rate R1, 0F0H. That is, move the contents of B. B register address is F0, 0F0. If you can remember from the SFR registers and general purpose registers addressing, we have a table in which that it shows each address of those registers. In that we have the B registers address as F0, and we need to mention that the initial letter should be a English letter, not a initial digit should be a digit, not the alphabet. That's why we have read 0F0 into RAM location whose address is held by R1. So the move the contents of B into RAM location whose address is held by R1. The contents of B register will have some contents. The data has to be moved on to the R1 registers mentioned address. R1 is already contains some data, that is some binary digits that will represent the another address in this memory location. So that memory location is filled by this contents of B register. MOVX @dptr, A writes the contents of the accumulator to the address held by the dptr register. Contents of accumulator will be transferred, that is to the address held by the dptr register. This is possible because dptr, A we are not directly moving the contents of a 8-bit to contents of, that is the 16-bit size of dptr, but we are doing what dptr has some value which will represent some memory location. That memory location is 8-bit, so the 8 bits of a register will be transferred into that particular 8 bits place. So this is possible. Note the important points: if the data is inside the CPU, only registers R0 and R1 are used for this purpose. The data is inside the CPU, only registers R0 and R1 are used for this purpose. When R0 and R1 are used as pointers, that is, when they hold the address of RAM location, there must be preceded by the sign. In the absence of the sign, move will be interpreted as an instruction moving the contents of register R0 to A instead of the contents of the memory location pointed out by R0. So in this indirect addressing mode, we should represent that with the help of a symbol. If we don't use then it will be assuming some other addressing modes already we have discussed: immediate and direct addressing mode, or it can be register addressing. The external RAM can be addressed indirectly through dptr. External RAM, in the previous example, that is move @dptr, A, that MOVX that is MOVX. So the external RAM can be addressed indirectly through dptr. The fifth point, indexed addressing mode. If you want to quickly revise this fourth register indirect addressing mode, just go through it. In indirect addressing, if you encounter the word indirect, just remember the symbol @. For immediate, it should be hash, that is the pound sign. For indirect, we should have @. In indirect addressing, the instruction specifies a register which contains the address of the operand. Both the internal and external RAM can be indirectly addressed. Examples of move a, @r0, move @r1, 0f0h, and MOVX @dptr, A. Next one is, this fifth addressing mode is indexed addressing mode. See, remember the names, right? First one is immediate addressing mode, second one is direct addressing mode, third one is register addressing mode, fourth one is register indirect addressing mode, fifth one indexed addressing mode. Only program memory can be accessed with indexed addressing. Either the DPTR or PC can be used as an index registers. Index with respect to some registers. Relative examples are move C a comma at the rate a plus DPTR at the rate a plus DPTR. Yes, it is allowed, because copy the what it will do, copy the code a byte, sorry, copy the code byte found at the ROM address formed by adding a and the DPTR to a. The RAM address where we have to copy this code, move C means move copy. The address where we have to find the adding a and the DPTR to a. Move C a at the rate a plus PC. Copy the code byte found at the ROM address formed by adding a and the PC plus 1. Adding a and the PC plus 1 has to be added, and whatever we have got, that should be used the address where we have to copy that code byte. Sixth one is register specific addressing mode. In this addressing mode, the instructions always operates on implied register such as A or DPTR. Therefore, no operands have to be specified. That is, the operands are implied. That means they are mentioned in the internally, not externally. Examples are RRA, rotate right accumulator. This instruction operates only on the accumulator. This instruction, when executed, rotates the contents of accumulator 1 bit towards right. And next example is DAA, decimal adjust accumulator. This is used in the case of BCD operands. The decimal values has to be adjusted to actually for the BCD format. And the next topic is need for bit level addressing. So with these 3 slides we can conclude the second chapter. Yes, this is a small chapter compared to the remaining 5 chapters, so it is completed somewhat earlier. And the last topic is need for bit level addressing in an 8-bit microcontroller. The minimum size of data that can be accessed or processed at a time is 1 byte. That is entirely 8-bit. But in many real world machine control applications, we may need to manipulate only 1 bit at a time. Okay, in the real world we need to access only 1 bit at a time. For example, sensing the state of a switch, that is on or off, make decision based upon the state of the switch. State of the switch is either on or off, that means either 1 or 0, that is a single bit. So to know that state, we need a single bit access is sufficient. No need to access the 8 bits or entire bits. Okay, and turn on or off the external device. Such operations need to manipulate only required bits of a byte. Such operations need to manipulate only required bits of a byte. If we perform these operations by accessing whole bytes, we should manipulate only required bits of byte without disturbing other bytes, which demands additional efforts and care for the programmer. Okay, so that is the main thing, because if we need only single bit, then we should access only single bit, not the entire byte. If we access the entire byte and we should perform something on that bit, it may alter the other parts, that disturb the other bits. So we should keep the bits unaltered, undisturbed. So this requires some extra attention in every step while we want to access the data of the single bit. The 8051 simplifies above mentioned problem by providing unique and powerful feature, that is single bit addressability and single bit operations. So it will support both single bit addresses, that means addressability of single bits, and single bit operations also allowed, that is the instructions on single bits also possible. It contains a complete boolean processor. It is a single bit processor and its instruction set to is optimized for the single bit operations. So single bit operations has to be function in order to use them effectively, efficiently. And in case of if you don't want to alter the data of the other accessible bits alongside with this required bit. It supports set, clear, complement, and or single bit operations. Set bit, clear bit, complement the bit, and the operation bit and or operation bits. The feature makes the 8051 one of the most obvious choice for industrial machine control applications. So that's why we have used 8051 in many applications in the real world. Bit processing operations provide the following advantages. So what is the advantage? That is faster execution of a program. A program will be fastly executed, less memory required by a program. So obviously the instead of bytes we should access only the bits. That obviously requires lesser memory space. Program listing becomes simple and more readable. So program listing becomes simple and more readable. So this is the topic of bit level addressing. We have the option of bit level addressing in this case of 8051, if you remember from the topic of internal memory organization of 8051, where we have internal RAM is divided into 3 segments. The second segment is the bit addressable area. After 32 lower bytes, the remaining 16 bytes are bit addressable areas. And such features are combined with the bit addressable operations and instructions which support bit addresses. So with this, 8051 will be effectively used in the machine control operations in the real world, because in the machines we will use some of the switches, buttons, power supplies, ons and offs, whether we have test some input, that whether it is giving or not, whether it is achieving it not. That means yes or no questions, either zeros or ones of a single bit. Then we need one bit only. In that particular operations, the bit addressability is a huge benefit to the programmer, and the machine is also becomes faster. So that will be an added advantage. And some of the operations in this 8051 for bit operations, that is set bit, clear bit, complement the bit, and operations also bit level operations. So advantage is faster execution, less memory, and program listing becomes simple and more readable. So with this we have completed the second chapter of microcontroller programming, electronics and instrumentation subject of C18 curriculum. The subject code is E8402. Please revise, recap, and remember the first two chapters video lessons, because in the third chapter we should write the programs. That means we should follow the sequences and the instructions also. We should learn each and every instruction, how it will work, where the data will be processed, how the data will be processed, and where it will be saved. So all these things we need to understand. So for that, the knowledge of these two chapters is essential. If you do not understand any topic, or if you can't remember those things, please revise all these video lessons till today before watching the tomorrow's video lesson, that is about the third chapter of 8051. Okay, so students, revise all those video lessons. With this, I conclude today's lesson. Thank you one and all. If you have any doubts, please mail me at sureshakul2001 @gmail.com. Thank you.